Alright, welcome back to the AI Research Roundup. I am your host, Alex. Today, we're looking at a paper called MUSt3R, which stands for Multi-View Network for Stereo 3D Reconstruction. This field is all about creating 3D models of a scene from a collection of 2D images. This paper builds on a previous model called MUSt3R, which had a key limitation. It processed images in pairs, making it very slow for large sets. MUSt3R solves this by handling multiple views at once, directly predicting a unified 3D structure for all images in a common frame. And if you want to dive deeper, the authors have released the official code for this work. The repository has pre-trained models, instructions, and even demos for things like visual odometry. Visual odometry is a technique for estimating a camera's motion over time just by analyzing the sequence of images it captures. So it's great to see that included for people who want to experiment with the model's capabilities in real time. But let's get into the architecture itself. So to see what this actually looks like, this first figure gives us some really nice qualitative examples. These are 3D reconstructions called point clouds, where each tiny dot represents a point in 3D space. The top image shows an outdoor scene from the Aiken Day-Night dataset that was processed offline. This means the model saw all the images at once to build the scene. The bottom image shows an indoor room, processed online, receiving images one by one. That winding path of boxes shows the camera's estimated motion, which is that visual odometry in action. So, how does the model actually build those impressive 3D scenes? This next figure gives us a peek under the hood at the uncalibrated reconstruction framework. Uncalibrated here just means the model figures out the camera's properties, like its focal length, all on its own. On the left, a single image frame is fed into the main MUSt3R model. The key innovation is this latent memory. You can think of it as the model's short-term memory, where it stores compressed information from past frames to understand the scene's context. It then produces both a global and a local prediction to build out the final 3D scene. Okay, so let's dig into how that latent memory actually works at a deeper level. This diagram shows the core architecture. On the left, we see the initialization, where the model starts with two images. Each image passes through a series of decoder blocks, which basically translate the image's features into 3D information. At each stage, the decoder from one image shares information with the other. This shared knowledge then forms the initial multi-layer memory. Then, on the right, when a new frame arrives, it uses that stored memory to inform its own calculations, and then updates the memory with its new insights. And that powerful memory mechanism is what allows the model to tackle some incredibly complex, large-scale environments. To give you a better sense of that, this next figure shows several more qualitative examples, this time from the Cambridge Landmarks dataset. We can see the model reconstructing the detailed architecture of these really large, intricate buildings. And just like we saw before, those winding paths of little boxes show the camera's estimated trajectory. The main takeaway here is just the impressive scale and complexity that MUSt3R can handle, building these detailed 3D models from a simple video sequence. So we've seen the model handle these large, intricate buildings. But what about more everyday, cluttered scenes, or when the camera is moving in more complex ways? Well, these next examples from the MIP 360 dataset show exactly that. We're seeing everything from a garden patio, to a bicycle propped up in a room, and a pretty messy kitchen. What's notable here is the camera motion. Those little black squares form these really complex, sometimes almost spherical paths around the objects. This demonstrates the model's robustness in handling these more unstructured, in the wild types of videos. And that robustness extends to another common real-world challenge: varying camera properties. This next set of examples from datasets like ScanNet++ and TEM-RGBD highlights the model's ability to handle varying focal lengths. A camera's focal length is basically its field of view, or how zoomed in it is. The fact that MUSt3R can produce these clean reconstructions of various indoor spaces, and even a backyard, without being told the camera's zoom level beforehand, is a really powerful demonstration of its uncalibrated reconstruction capabilities. To wrap things up, what the MUSt3R paper really shows is a significant step forward for 3D reconstruction from video. By using a powerful memory-based approach, it can create these incredibly detailed 3D models from uncalibrated cameras, even in large, complex, and cluttered environments. This work brings us closer to a future where anyone can capture the 3D world around them using a simple video camera. Thanks for tuning into the AI Research Roundup. I'm your host, Alex.